Good morning, sir. I'm K. Vendela. I'm from CSC Department of AML. My roll number is 259558626. Today, my topic is the wild side AI. First, introduction to wild side AI. The wild side AI is a smart wildlife monitoring system that uses camera traps, sensors, and AI to track animal behavior in natural habitats. It integrates computer vision models with a robust database backend to store, query, and analyze ecological data efficiently. And the system supports real-time species identification, population tracking, and habitat change detection over time. And the design for conservationists and researchers, it reduces manual efforts in data collection and it improves the accuracy in biodiversity studies. And next, the wild-side AI exemplifies how database systems can empower AI-driven environmental application at scale. This is the introduction to the wild-side AI, and we can go through the system architecture overview. The wild-side AI follows a three-tier architecture that the first one is data acquisition layer, and second one is the processing layer, and the third one is the database storage layer. The camera traps and IoT sensors captures images and environmental data, which are transmitted to edge devices for pre-processing. And the processing layer runs lightweight CNN models to classify species and detect anomalies before sending metadata to the central database. And this all processed data is stored in a relational database with a time series support for the efficient querying and reporting. The architecture ensures scalability, fault tolerance, and low latency access for field researchers using web or mobile interfaces. This processing of the layers are used by the lightweight that convolution neural network models that process the images and videos in the internal layer and give the output. That these anomalies are before sending metadata, they are sent to the central database. And this can be used by the camera traps and IoT sensors that captures the images and environmental data. And the wild-side AI follows the three-tier structures, the data acquisition layer, and the processing layer, and the database storage layer. And next, data sources and types. Primary data sources include motion-activated camera traps, acoustic sensors, GPC collars, and weather stations deployed in forests. These are the primary data sources that can include the camera traps that use it to motion activated, and the image data consists of time-stamped photos or short video clips tagged with location, temperature, and humidity readings. The metadata includes species labels, confidence scores from AI models, and bounding box coordinates and behavioral annotations. These are the metadata. And the time series data such as animal movement patterns and seasonal activity cycles are also collected and stored. These all data types are structured to support both real-time alerts and a long-term ecological trend analysis. These are the primary data sources that use the activation of motion, and the consisting of images have the data like location, and the temperature of the photos and the humidity readings are included. And the metadata includes the species labels and the bounding box coordinates. And we have the time series data such as the pattern of the animal movement and the seasonal activity cycles are also collected and stored for these data sources. And next, relational schema and normalization. The logical schema includes tables like animals that animal ID, species, conversation status, and the cameras contain the constraints like camera ID, location ID, and status. And the observation constraints are observation ID, cam ID, and animal ID, timestamp, and confidence. These schemas include these constraints that every has the relational and the Normalization up to 3 NNF eliminates redundancy. For example, species names are stored once in animals, not repeated in every observation. Foreign keys enforce referential integrity between observations, cameras, and animal tables. Indexes are created on timestamp and location ID to speed up time range and spatial queries. The denormalizer views are used sparingly for reporting, balancing performance with data consistency. These are the relational schema and normalization, that the logical schema that includes the database and the constraints that include the relation of them. And the 3 NNF normalization are used to eliminate the redundancy, that species names are stored once in animals, not repeated in every observation. By the normalization, the schema can be reduced and it can be easily used. The foreign keys enforces the referential integrity between observations, cameras, and the animal tables. It can reduce the data of the tables that eliminate the redundancy, and the indexes are created on timestamp and the location ID to speed up the time range, and the denormalized views are used sparingly for reporting, balancing performance with the data consistency. This is the relational schema and normalization. Next, AI integration with database workflow. The raw images from cameras are first processed by an on-device CNN models, that are convolutional neural network models that mobile net to detect and classify animals. The CNN models that consist of the input layer, internal layer, and output layer that processes the images and videos. The neural network is used. The examples are mobile net that to detect and classify animals. Here we are using the animals images, that the raw images from cameras that processed on devices that use the CNN models. Only high confidence detections, example greater than 85%, are sent to the central server to reduce bandwidth and storage load. The AI model outputs species, bounding box, confidence score are inserted into the observations table via API calls. The low confidence detections are flagged for human review and stored in a separate pending review table. Model retraining is triggered periodically using label data accumulated in the database, creating a feedback loop for improvement. This is the AI integration with the database workflow that captures the raw images of the animals that use it to classify and detect the what kind of animals, and it can be first processed on the CNN device models, and it only detects the above 85% or sent to a central server to reduce the bandwidth, and the AI model outputs or species are inserted into the observations table via API calls, and the low confidence detections are flagged for human review, and the model retraining is triggered periodically using label data accumulated in the database, and it can create a feedback loop for improvement, and it only contains the high confidence detections, and this is the AI integration with the database workflow. And next, indexing strategies for performance. B-tree indexes are used on timestamp and animal ID columns to accelerate range and equality queries. Composite indexes on that, like location ID, timestamp, optimize spatial temporal queries like show all deer sightings in forest that last month, and it has the full text indexing supports searching observational notes or researcher annotations for keywords. Partitioning by date, that example monthly, it improves query performance and simplifies archival of old data. Index usage is monitored and tuned based on query execution plans to avoid overhead on write-heavy operations. That the B-tree indexes are used on the timestamp and the composite indexes on optimized spatial temporal queries, and the full text indexing supports searching observational nodes, and the partitioning like a date, a month, a year, that can improve query performance and simplifies retrieval of old data. By partitioning by date, it can achieve the old data that recorded and it can improve the performance. So the index usage is monitored and tuned based on query execution plans to avoid the overhead and that can use to write the heavy operations. This is the indexing strategies for performance. And next, querying wildlife data. That examples, we can see the examples that researchers can query total sightings per species using group by and count on the observations table. The time series analysis identifies peak activity hours by extracting hour from timestamp and grouping observations. The spatial queries use joins between observations and locations to find the animals that near to water sources or trails. And the trend queries compare yearly population estimates using window functions over partition time ranges. And complex queries combine AI confidence thresholds, weather conditions, and the species behavior for deeper insights. These are the examples for querying wildlife data. And next, data integrity and security. The ACID properties ensures that observation records are either fully committed or rolled back during system failures. And the audit logs track who accessed or modified sensitive data, and it supports the compliance with environmental data policies. Data encryption is applied at rest, that at a database level, and in transit, the TLS for API communications. And the role-based access control restricts data access that field staff can insert observations while analysis have read-only access. And the data encryption is applied at rest and in transit. And the regular backups and geo-replication protect against data loss due to natural disasters or hardware failures. This is the data integrity and security. And next, scalability and cloud deployment. The WildSite AI uses a cloud-based PostgreSQL instance with read replicas to handle high query loads from multiple users, and the auto-scaling groups adjust compute resources during peak data upload times, such as after seasonal migrations. And the microservices architecture allows independent scaling of AI processing, database, and front-end components. And the containerization with Docker and orchestration via Kubernetes ensures consistent deployment across environment. These are the scalability and code deployment of the WildSite AI. And next, challenges in wildlife data management. High volume of image data requires efficient compression and selective storage to manage costs, and network connectivity in remote areas limit real-time uploads, necessitating edge catching and batch synchronization. And data quality issues like blurred images or false triggers must be filtered before database insertion. And long-term data retention policies must balance storage costs with the scientific value for longitudinal studies. These are the challenges in wildlife data management. And the case study that tiger conversation in Western Ghats is that WildSite AI was deployed across 50 cameras traps in a tiger reserve to monitor endangered Bengal tigers. And over 6 months, the system logged 1,200 high confidence tiger detection with timestamps and locations. And the project demonstrated how integrated AI and database systems enable data-driven wildlife protection. And the conservation teams used these insights to adjust patrol routes and reduce human wildlife conflict. And the future enhancements and research directions are integration of satellite imagery and drone data to expand monitoring coverage beyond ground level cameras, and use of graph databases to model animal social networks and migration paths as interconnected nodes. Federated learning to improve AI models across reserves without sharing raw data and preserving privacy. The development of public dashboards with interactive maps and trend visualization for policymakers and educators. Thank you.